All right, today's workshop is going to be about the groups of the periodic table, just some general information, and we're going to try to make sure you can mark up your periodic tables with this information if you have one. If you don't, you need to get your hands on one as soon as possible to make sure you can get this information out there. Okay, so periodic table groups. Um, First term is valence electrons, and in our Bohr model, you have your electrons on the inner shell, but then you have the ones on the outer shell. The valence electrons are those electrons that are on the outermost shell, and those are the ones that will do most of the bonding when we get into talking about bonding here in a couple weeks. So just understand that the valence electrons are the electrons on the outer shell, and that'll come up again and again. There's two groups, the periodic table, metals and nonmetals, and there's a third group, metalloids, that we'll identify. They kind of go in between metals and nonmetals, but there is a definite difference between metals and nonmetals, and here are some of the properties that make that stand out. The appearance: metals shiny, nonmetals dull. The hardness: metals very hard. Nonmetals are brittle. When I say brittle, that means they snap. Metals, on the other hand, you can bend them, but they're not going to snap, and that means they're malleable, right? That means we can bend them, while nonmetals, because they're brittle, are non-malleable. They shatter. Ductile: can be rolled into wires. Metals can be rolled into wires. Nonmetals cannot. Conduction: metals are good conductors of heat and electricity, while nonmetals are not. State: metals are almost all solids. There is one liquid metal that we talk about, and that's mercury. But nonmetals can be any state of matter, and of course their density, metals have a much higher density than the nonmetals. So those are some differences. Usually if you're dealing with one, the big ones are going to be the appearance and the conductivity, and that kind of explains what we use them for. So on the periodic table, and the first thing I want you to do is mark a stair step that looks like this, okay? And this isn't exactly like the periodic table I handed you, but the stair step goes to the left of boron, and then you just come on down and make the stair step. Anything to the left over here are metals. Anything to the right are nonmetals. And so this is the line that differentiates between metals and nonmetals. So make sure you can draw that stair step, and you know to the left and to the right what you see, okay? The other thing I want you to mark up right now is the number of valence electrons. This group right here, okay? Group 1, 1 valence electron. Group 2 with beryllium at the top, 2 valence electrons. Now, we're going to skip over transition metals, and we're going to go right here with boron and aluminum, and we're going to say 3 valence electrons. Not all of them, but boron and aluminum, 3 valence electrons. Group 14, carbon and silicon, for sure, 4 valence electrons. Group 5, nitrogen, phosphorus, arsenic, 5 valence electrons. I'm sorry, group 15. Group 16, oxygen group, oxygen, sulfur, selenium, tellurium, 6 valence electrons. Group 17, fluorine, chlorine, etc., all of these, 7 valence electrons. And in this last group, helium has 2 valence electrons, while neon on down has 8 valence electrons. Mark those down so you know how many valence electrons are in each group. The lanthanides, actinides, and the transition metals all will have varying transition metals, or varying valence electrons, and we'll get back to that in a second. So first group to talk about is the alkali metals. Soft, shiny. They have 1 valence electron, highly reactive. Reactivity increases as you go down a group, okay? So we'll kind of show this video here if it will play. And this first thing you're going to see is lithium. And this is lithium in water. And it kind of does some stuff. It moves around. Nothing really fancy. Obviously, you're not going to be too excited about that, but it does react. Sodium and water now. Again, very similar to lithium. If you light the hydrogen that's in there, you'll get a little bit more of a flame. You can actually see the sodium color that you saw from the flame test. Potassium. Again, this is going down the periodic table of the alkali metals. Potassium, putting it in water, doesn't need any help. It instantly ignites. And you can see again, instantly ignites. Rubidium, putting rubidium in water, and that almost looks like a firework, doesn't it? And then cesium in water. Very explosive. So as we talk about alkali metals, reactivity does increase as you go down the group. Okay, so here's the periodic table. This is your first group, so this is the alkali metals. So make sure you know where that group is. Again, 1 valence electron. Alkaline earth metals, shiny silvery white metals, 2 valence electrons, low densities, low melting and boiling points, a little bit different than the alkali metals because they're not as reactive. The alkaline earth metals, again, are right here, beryllium on down, the whole group. Transition metals. Well, when we talk about metals, transition metals are what they are, your typical metals. They're good conductors with high melting and boiling points, and their number of valence electrons will vary. Again, your typical metals. And you can see this whole group here, right? And I even include all of these. So I say, it's all these here, but I also include these with zinc and cadmium and mercury, and some of these I'll talk about later. But all of these, like copper, gold, silver, things that we consider metals in general terms, are the transition metals. And again, their valence electrons do vary. Lanthanides, very magnetic. Used in MRIs and lasers. Rubidium is probably one of the best magnets you can get. You get one of those, man, it'll stick to anything and be hard to pull apart if it's a good magnetic field. But the valence electrons also will vary. So the lanthanides, and this one's interesting, it starts at number 57 and goes all the way to 71. So here's your lanthanides right along here. Actinides are radioactive. They're used in nuclear reactors and weapons, among other things. You can find actinides in smoke detectors too, so they're not all weapons of mass destruction here. But the valence electrons will vary, and your actinides are down here in the pink. Again, they start at number 89 and go to 103. The post-transition metals, they're a little different than the regular transition metals. They just have a little bit lower boiling and melting points, but they still do some of the same things, and that's these right here. Okay. We'll do some things a little bit different, but that's tin, lead, and if you've ever dealt with lead, lead's a lot softer than gold and silver and copper, right? And that's just one of the things that makes them stand out, but they're still considered transition metals. The metalloids. So on your periodic table, you want to put boxes around these, around boron, silicon, germanium, arsenic, antimony, tellurium, and polonium, and they vary. They're right along that stair-step line, so their properties vary between metals and nonmetals. What they do is that they conduct really well in extreme conditions, which means they're really good for computer chips. Your computer gets hot and they'll still operate. Bakeware, they will still hold their shape when you cook something really hot, or like Pyrex, where you can it's glass that you can get really hot and cool down right away, and it doesn't shatter. And of course, semiconductors, which work kind of like computer chips. So the metalloids, again, boron, silicon, germanium, arsenic. And then you got all the way along here, okay? So make sure you put boxes around those on your periodic table, and you can see it's right here along that stair-step line is where the metalloids are at. Other nonmetals, they're definitely the opposite of metals when we talk about their properties. They're good insulators, so they don't conduct very well, and they're brittle. They shatter. I use carbon here as an example. Carbon's like pencil lead or graphite. It just snaps when you try to bend it, and that's because it's brittle. So your other nonmetals are right along here, these green ones. So as you slide down that aren't metalloids are right here. And then we're going to talk about these two groups next. The halogens, highly reactive. They're harmful to biological organisms, and they have 7 valence electrons. These 7 valence electrons are what makes them so reactive. Okay, having 7, having 1 are two very important things. So these have 1 valence electron in the alkali metals, very reactive. The halogens, 7. Now, when we say harmful to biological organisms, think about these things. Fluorine, fluoride. Fluoride, put it on your teeth. It helps protect your mouth when you go to the dentist from bioorganisms growing on your mouth and hurting your teeth and gums and your enamel. Chlorine, used in pools, You use it with any kind of a disinfectant. Bromine, iodine, same thing. If you ever had surgery done, they put iodine all over the cut after the surgery is over, and that's to be sure that it will kill any bacteria that could try to form. So these are biological killing organisms, but 7 valence electrons, and they're called halogens. Group 8, the noble gases. Odorless, colorless gases, very low reactivity. In fact, they're considered inert, is the word, I-N-E-R-T. Usually if we have something that's reactive, like an alkali metal, we will try to store it in a noble gas so it won't react. Now, valence electrons, we kind of talked about this. Helium has 2, but the rest of the noble gases have 8 valence electrons. So I kind of go back here a little bit. There's your groups. Make sure you can mark them, okay? Make sure you have the valence electrons written down. Make sure your stair steps there. Make sure you put boxes around your metalloids. That will just help you along the way, okay? So I'm expecting you to do this on your own. You can color code it if you want to. It's not necessary. If you can find a way to put it on your periodic table, though, that will help you immensely. Let me know if you have questions.